Hi, 6th grade. Welcome to your kind of long lecture on stars. Go ahead and get the slides pulled up. When you look at it, you'll see that it's 3 whole sections in the book, but I've pulled out the most important information for all of it. So your warm-up is if something has an apparent magnitude of -17 and another object has an apparent magnitude of 4, which object appears brighter? So go ahead and take a second to answer that. And if you said negative, you're correct. So the more negative a number is, the higher apparent magnitude it has, and it appears brighter to us. So as I said, this is chapter 12, pages 142 through 147. And let's move on to slide 3. So we already talked about apparent magnitude. And apparent magnitude is our perspective of an object from Earth, how bright it seems to appear. The opposite of apparent magnitude is absolute magnitude. It's not based on our perspective, it's a measure of the actual brightness of this object that you're looking at. The brightness is dependent on size and temperature of the object, and what this brightness is, it's produced by the light that these objects emit via nuclear fusion. We learned nuclear fusion back during our whole chemistry lessons, and it's where something comes together. The nuclei fuse to form a new one. It does use the same scale as apparent magnitude, but it's just the actual measurement. And in this process of the nuclear fusion of emitting all of its light, what happens is all of the materials inside the objects, they were saying a star, they're burning. And as it starts to burn all these materials, remember in nuclear fusion, a bunch of energy is going to be output. And it's, in this case, it's output as light, as photons. So when we talk about stars, you've probably heard the terms white dwarf, red giant, all that kind of stuff. And its color comes from how hot it is. It's how bright it is. So if you look at the little scale on the bottom of the slide there, you'll see that blue is the hottest. So a blue star is the hottest. It has a surface temperature of at maximum 50,000 degrees Kelvin. So that's a lot. On the opposite end, the red stars are the coolest stars, and they are at 2,500 Kelvin. So that was all about absolute magnitude, that first little section. Now we're going to go into star populations, the next section, pages 144 to 145. There are multiple types of stars out in the universe, and we have something called the HR diagram that groups stars together into populations. And it's a diagram that you can look in your book. It's on page 144. That it compares an object's absolute magnitude, surface temperature in Kelvin, and its luminosity as compared to our sun. The luminosity is simply the amount of light emitted per second by this star, and it's a graph that has 3 axes. On the left-hand y-axis, it's the absolute magnitude. Then the x-axis is the surface temperature, and the right-hand side y-axis is the luminosity. There's a copy of it there on the screen. What this diagram does is it allows us to estimate the size of the star, because stars are really far away and we can't actually go there, like measure it with a measuring tape. It's not going to work. It's a ball of gas. It's too hard to directly observe them. So using this chart, you can estimate how big something is that you're looking at. So continuing with star populations, any placement within this HR diagram shows that most stars fall together in this diagonal section that I circled. 90% of the stars that we know of fall into this section. It's called the main sequence section. They're all small to medium in size. And our sun does fall in the main sequence section. It's actually one of the little yellow dots down in that picture. And in a second, we're going to talk about things that are outside that circle. So if you go on to slide 6, the other stars that are shown in that diagram are white dwarfs, giants, and supergiants. White dwarfs, like the Sirius B star, are very small, very hot, and very dense. That's why they're down in the left-hand corner of that chart. Giants are large, hence their name. They're bright, so high luminosity, and a high, so the giants have a high magnitude as well. These are usually red in color because they have a low surface temperature, and they exist up in that upper right-hand portion of the graph. Then we have supergiants, which, based on their name, they are super big. They're really, really big. They have a wide variety of temperatures, and as I said, they're just really big. So if you move on to slide 7, this is starting with star life cycles. And astronomers have observed stages in stars, which is hinting at what their life cycles are like. And it's pretty simple to break down before we break it down. Step 1 is the star's birth. Step 2 is the whole main sequence. Then step 3 is its death. So let's move on to slide 8 and start talking about star birth. A star's life begins in a nebula, which is a large cloud of gas and dust out in space. And you can think of it as like a nursery for stars. You can see a picture of the Eagle Nebula on the right-hand side of the slide. So in a really dense part of a nebula, gravity is pulling gas and dust all together, forming what is called a protostar. It's kind of like a baby star. And this protostar starts building and building and building until it's capable of nuclear fusion, which is, you know, what stars do constantly. So it needs to become very hot and very dense to start performing fusion. So that's how a star begins. In a nebula, little primary stages, and then it builds up enough to become a star. So during the main sequence of a star's life, this is slide 9, it's the longest stage in which the star is living. And it goes on and on and on and on until it starts beginning to run out of fuel for its nuclear fusion. And that's pretty much the whole main sequence. It kind of just exists and has nuclear fusion occurring for the longest time, and then it's going to start to lose fuel, and that's when the star begins to die. At that point, it will turn into either a giant or a supergiant, depending on the size it was before. Small, medium stars become giants, and the biggest stars that are out there become supergiants. So if a supergiant, after the star turns into one, if that explodes, that's called a supernova. And what happens is all the materials just start spreading out, and it glows even brighter for days. So when a star begins to die, what happens, it's running out of fuel, its core shrinks smaller and smaller, and the outer portions expand. And again, if it's a supergiant, it can explode and create a supernova, which will keep spitting out more and more material, maybe create new nebulas, and then we're going to move on to the final stages of a star's life into death on slide 10. So if there was a supernova, or just all the material spreading out into space, all that's left after a star dies is a very small, dense object. It's either going to become a neutron star, which we'll get into in a second, or a black hole. You've heard of those before. A black hole is very, very dense, has very, very strong gravity, and it pulls everything in around it. It's trying to suck all the stuff that's into its center. And it's called a black hole because light cannot escape it. Everything's getting pulled in by so much gravity that you can't actually see them. Scientists can find black holes by reading measurements out in space and seeing, oh, well, there's a appearing to be nothing there, but there's lots and lots of gravitational pull, so that must be a black hole. And because light can't escape it, we don't actually know what they look like. So after that supernova and whatever's left, if it's a neutron star, all the material spreads out to form some brand new nebulas. Maybe they become a star nursery and start birthing other stars if the material can be dense enough and contract. And now we're going to talk about neutron stars, which are on slide 11. So this is what could be left behind by a supernova. It's just the really small, dense core of the supergiant if it didn't become a black hole. And the reason it occurs is because the matter in the star collapsed due to so much gravity in the environment, and it created this whole new star. Neutron stars are similar to white dwarfs, but they have 2 to 3 times the mass of our sun. So like, imagine you're holding a penny that represents like, or maybe you're holding a kitten, and then you're holding another kitten, but that kitten has 3 times the mass as the other kitten, and it's just really, really dense. Some of these neutron stars can rapidly spin. They'll just spin on an axis, and they emit these radio waves called pulsars. So, I mean, the radio waves are not called pulsars, I apologize. The spinning neutron star is what the pulsar is. So, that's it on stars. That was a lot of information to dump on you, but all you have to do today for homework is to read those pages, and hopefully I explained it well enough. Have a good day.